Right. My apologies for the breaking transmission. As I was saying, a very good afternoon, good evening, good day, warm welcome to the South African National Space Agency. We are thrilled to have you join us this afternoon for our Science of Space talk for June 2022. We have a very exciting topic this afternoon to share with you, the science of space weather, and it's given by a great friend of the Space Agency, Patricia Doherty. Patricia is the Director and Principal Scientist of the Institute of Scientific Research at Boston College in the USA. As Director of the Institute, she oversees the activities of staff members working on a variety of innovative research projects. These projects include studies of space physics, space weather, ionospheric and atmospheric effects on space-based systems, ionospheric measurement techniques, chemical reactions in space, and magnetospheric physics. As a scientist, Patricia's own research interests are centered on space weather and ionospheric effects on global navigation satellite systems and its relevant applications. In addition, Patricia has been very active in promoting research and education in the science of navigation in developing countries. She is an associate editor of the Radio Science Journal, a member of the American Geophysical Union, past president of the Institute of Navigation, vice president of the International Union of Radio Sciences, OSI, chair of the NASA Space Weather Council, and secretariat of the Scientific Committee of Solar Terrestrial Physics. She is the recipient of numerous awards for research and international outreach, including the Ian Burkle Award, the Ian Wems Award, the Ian Distinguished Service Award, the 2017 GPS World Leadership Award, and the 2018 AGU Carrington Education and Outreach Award. She's a fellow of the Institute of Navigation and a fellow of the African Geospace Society. And as I mentioned at the beginning, Patricia is a good friend and colleague, and has been associated with the South African National Space Agency for many years. And in fact, almost 3 years to the date, she gave a presentation similar to this in person in Hermanus. And we are very, very grateful and happy to have her join our Space Talk again this year. So Patricia, thank you very much for giving up your time to talk to us. And I'm sure you're going to inspire the people on the call as much as you've inspired the young people in SANSA. Thank you very much.
Thank you, Leanne. Shall I share my screen? If you don't mind, I will turn off my video because my home network stalls sometimes that it's on it, but I'll join you in video when this is through. So thank you once again. Just someone tell me, can you hear me okay?
Yes, we can hear you fine. But...
Okay, great, thank you. So thanks, Leanne, once again for your kind introduction and your friendship. And thanks to all of you for joining us today. I'm really honored to be the speaker for this Science of Space Talk, which will focus on space weather, one of my favorite topics. To begin, this picture really sums up what space weather really is. Space weather begins inside the sun and it ends in the circuits of man-made technology. Not going to the next slide. Try that. Okay. In fact, space weather includes really any and all conditions and events on the sun, in the solar wind, in near Earth space, and in our upper atmosphere that can affect spaceborne and ground-based technological systems and through these, our human life and endeavors. Although space weather events have been an occurrence since the beginning of time, it's really only since the late 20th century that it became a big problem for all of us. And that's primarily as society has become dependent on space-based infrastructure. And with this increasing dependence on space-based infrastructure, space weather has become more and more important for general understanding and to have plans to define, mitigate, predict, and all of these very large events. And this is what we'll discuss in this presentation. So the presentation is a relatively simple one. We'll look at some of the prime drivers of space weather. We'll investigate some of the more intense space weather impacts. We'll discuss some of the international collaborations in progress that are to forecast and mitigate space weather, and then we'll summarize. So to start, it's really important to note that the sun is the ultimate source of almost all of space weather. As we know, the sun lies at the heart of the solar system, where it is by far the largest object. It's very old, 4.6 billion years old, in fact. It's far away, it's 96 miles away from the Earth. It holds nearly 99% of the solar system's mass, and with a diameter of 864,000 miles, it's 109 times the diameter of Earth. In light minutes, it really is about 8 minutes from Earth. And it's really just a hot ball of plasma, really comprised mostly of hydrogen and a little helium. It is very powerful, as it would take 100 billion tons of dynamite every second to match the energy provided by the sun. And although it's quite powerful and central to life on Earth, it's really a rather ordinary star in the universe. As you can see in the bottom left, it is just one of the more than 200 billion stars in the Milky Way galaxy, some 25,000 light years from the galactic core. The sun, as shown in the illustration here to the left, is divided into 6 layers. From the center out, the layers of the sun are the core, the radiative zone, and the convective zone. And then there's the visible surface, which includes the photosphere, the chromosphere, and finally the outermost layer, the corona. The energy that's produced through fusion in the sun's core powers the sun and produces all of the heat and light that we receive here on Earth. But it's not just a big bright ball. The process by which that energy escapes from the sun is really quite complex, with complicated magnetic fields that form sunspots in active regions. The sun also sends out a constant flow of particles in the solar wind, and it occasionally erupts with giant clouds of solar material called coronal mass ejections, or explosions of X-rays in the form of solar flares. Now, these events can rattle our space environment out to the very edges of our solar system, and this is really the onset of space weather. But major space weather events, such as those coronal mass ejections and solar flares, they don't happen every day. In fact, the most significant events are closely tied to the peak of the solar cycle. This figure here shows the yearly mean sunspot count since 1700. These sunspots have been counted really since the invention of the telescope in the early 1600s. So the approximate 11-year solar cycle is based on the number of sunspots that are observed on the sun, with those high numbers referring to solar max and the low numbers, of course, referring to solar minimum. The 11-year cycle is tied to the time it takes for the sun's magnetic field to flip. This means that the sun's north and south poles switch places. Then it takes another 11 years for the sun's north and south poles to flip once again. So the sunspots are caused by the sun's magnetic fields, and as the magnetic fields change, so does the amount of activity on the sun's surface. So near the minimum of the solar cycle, it's rare to see sunspots on the sun, and the spots that do appear are very small and short-lived. And space weather events will be minimized, but they're not impossible. It is interesting to note that the most recently completed solar cycle 25, shown over here on the right, was the lowest solar cycle in over 100 years, only matched to the one that occurred in the early 1900s. That was solar cycle 14. So here's an image of the daily sunspot numbers from 2009 to the present. I'm really just showing you this to illustrate that there's a lot of variability in the number of sunspots on a day-to-day basis, not just an 11-year cycle basis. So in yellow, we're looking at the daily sunspot numbers. In blue, the monthly sunspot number, the monthly average number. And then in red, we look at the monthly smooth sunspot number. Those red dashed lines that you see over on the right are predictions here for solar cycle 25, and you can see they're quite different. Many solar scientists are predicting, what the peak of solar cycle 25 will be, and as you can see, they can be quite different. So I hope I've convinced you that space weather begins in the sun. In fact, it begins with the sunspot. These sunspots are visible on the sun as they're darker than the surrounding surface. They're darker because they're cooler, and they're cooler because of the intense magnetic fields within them. These magnetic fields are so strong that they keep some of the heat from the sun from reaching the surface. The figures on the left show just how visible these sunspots can be. In fact, that bottom figure just shows how big they can be by comparing it to the size of Earth. Solar active regions, shown in the middle section there, are regions where pairs or clusters of sunspots are associated with the release of energy from the photosphere. The exact mechanism that causes the explosive release is really unknown, but we know that they're related to the rapid conversion of magnetic energy to particle kinetic energy. And this twisting of the surface of these magnetic fields leads to the release of that energy. So these active regions are really the source of those solar flares and CMEs. So solar flares are one of the largest explosive events of our solar system. They're characterized by intense releases of energy in the form of radiation and electrically charged particles. So radiation can travel at the speed of light, while the charged particles move much more slowly. So there's three classes of flares based on X-ray energy. There are C, M, and X-class flares. The X-class flares are the strongest solar flares that the sun can unleash. And when aimed directly at Earth, they can disrupt our communications and our GNSS navigation systems on Earth. And they can even pose a threat to satellites and astronauts in space. So M-class flares are about the 10th the size of the X-class flares, but they can still supercharge the Earth Aurora or the Northern Lights, and they can result those in dazzling displays. But they can also cause some direct disruption to our near space environment. So here are some actual system impacts from the most intense solar flare that occurred in 2003. This is during one of the highest solar cycles in our recent history. This flare saturated X-ray detectors on several monitoring satellites, resulting in the loss of Japan's Midori satellite. There were anomalies seen on at least 30 other satellites, and effects were felt on 2/3 of all of the NASA satellites. Also, the FAA issued its first ever passenger alerts for possible exposure to radiation. The FAA's Wide Area Augmentation System, which is a civil aviation system that utilizes GNSS satellite navigation, also saw errors exceeding 100 meters. We also saw that satellite communication systems were interrupted and electric power service failures were found in Sweden. Once again, this was perhaps one of the largest solar flares that was ever recorded. So coronal mass ejections are really intense, even more intense solar events that are characterized by huge bubbles of plasma that are ejected from the sun and speed into space. They do disrupt the flow of solar wind, and they produce disturbances that can strike the Earth with sometimes catastrophic results. These occur over large sunspot groups and are most often associated with large solar flares. CMEs are truly the most threatening of solar events on our technological systems, as they can induce geomagnetic storms on Earth. They typically reach Earth in 1 to 5 days after the eruption on the sun. The pictures on the right show CMEs are recorded on January 1st, 2002, and then an earlier one on the bottom from 1998. These pictures are from the SOHO images, each showing enormous eruptions of those CMEs spreading out into space. Last but not least, there's the solar wind. Solar wind is a very important space weather phenomena. It is the phenomena that carries that solar atmospheric mass, momentum, and energy that's due to those solar flares and CMEs into space. The solar wind streams in all directions and changing speeds, and it moves faster over coronal holes, and it's slower at low latitudes. The source of solar wind is the corona. The corona, as I mentioned earlier, is so hot that the sun's gravity cannot hold on to it. Finally, as that solar wind buffets the Earth's magnetic field with tons of plasma from CMEs and flares, it can produce solar magnetic storms on Earth. So this is a classic case. It's an animation from NASA of a magnetic storm. These large solar flares and CMEs induce solar storms on Earth. They're typically in response to those very large events that burst from the sun with great speeds, carrying billions of tons of plasma into the solar wind. That Earth's magnetic field generally deflects much of this solar wind, as shown here. But under intense conditions, those particles can enter the Earth's magnetic field where those lines connect on the anti-sunward side of the Earth. And this results in Aurora, which you can see lighting up right there. also results in a geomagnetic storm. The effects of these storms include degradation of satellite instruments. It introduces dangerous particles to electronics and to people. It disrupts GNSS and satellite communication, and it has the potential to introduce drag on satellites, changing their orbit paths. And finally, there are effects on GPS for positioning. So the animation that I just showed in the last slide depicted a very strong magnetic storm. This is the interaction between the sun's plasma, Earth, wind, and Earth's magnetosphere, and basically refer to this as the sun-Earth connection. The solar wind is constantly flowing, but the Earth's magnetic field deflects it under normal conditions. But under intense conditions, such as what you just saw, those particles can enter the Earth's magnetic field where the lines connect on the anti-sunward side of the Earth. The side of the magnetosphere that gets hit by the solar wind is called the day side magnetosphere because it faces the sun. The part of the magnetosphere that stretches back as though it was streaming with the solar wind is called the magnetotail. Note too that this solar wind doesn't just come towards Earth. Solar wind and all of those particles go in all directions and can reach out as far as Pluto and Neptune. It's important to note that not all geomagnetic storms are caused by flares and CMEs. Coronal holes are another source. These appear as dark areas in the solar corona in EUV and soft X-ray images. They are cooler, less dense regions than the surrounding plasma, and they are regions of open unipolar magnetic fields. So this open structure allows charged particles to escape, resulting in streams of relatively fast solar wind, and it can result in geomagnetic storms. And these are the prime sources of storms during solar minimum. But note that they're not as severe as the storms that are caused by CME closer to the peaks of the solar cycle. So one of the more benign consequences of space weather is a pretty one, and these are the aurora, which we know better as the northern and southern lights. A bright aurora signifies that a strong disturbance in the upper atmosphere in the magnetic field has happened. This happens when excited particles from the magnetosphere collide with particles in the Earth's upper atmosphere, and it electrically excites them to emit light. Aurora usually appear between 60 and 80 degrees latitude, and it expands equatorward under intense conditions. Finally, the aurora, is the only visible sign that the Earth's magnetosphere has been disturbed. However, much of what we call space weather is invisible to the naked eye, and it can have much more severe consequences. One of those consequences is radiation. Radiation can be a big problem, primarily for air travelers. In fact, a major source of radiation exposure from air travel comes from the flight itself in the form of galactic cosmic rays. The figure on the top shows the smooth monthly sunspot averages from 1960 to 2009, shown at the top of that plot, together with the counts of the galactic cosmic rays recorded in Antarctica by the University of Delaware. Here we see that those galactic cosmic rays are really anti-correlated with solar activity, so they're basically not really a space weather phenomenon. However, when these galactic cosmic rays are combined with episodic eruptions from the sun, they'll produce and scatter additional high-energy particles into broad ionizing showers, producing additional harmful radiation effects. The figure I'm showing here now on the top right really shows you the amount of radiation that you can be exposed to during a normal commercial flight. Typical aircraft, right here, fly at about 30,000 feet. And those are exposed to approximately 3 microsieverts per hour. This is a measure of radiation exposure. What I'm told by the medical community is that's similar to what you'd get in a normal chest X-ray. However, when you go to higher altitude, you can see that the exposure increases. And it's because at high altitudes, the air gets thinner. And thinner air then means that there are fewer molecules to deflect those incoming rays, that radiation from space. So this is particularly risky to high altitude flights, to astronauts in travel, and to the International Space Station occupants. Although the International Space Station is shielded to protect its residents from these storms, future space flights that we talk about now to the moon or Mars are going to require something more protective. Radiation from space weather events is also risky to commercial flights flying over the poles, where there's less protection from the Earth's magnetic field. During solar storms, airlines have to reroute the high latitude flights to avoid this increase in radiation, but it's a very costly process. Several years ago, we found that those flights redirecting those flights can cost well over $100,000. Other effects of space weather include damage to our satellites. Some of the problems that occur are energetic ions that can damage solar panels, energize plasma, that can cause electrical charges that can damage the electronics. It can increase satellite drag, which would knock a satellite out of its orbit. And with the economic loss, there could be potential for great economic loss because the satellite enterprise is valued at being well over $100 billion. Some of the actual events in response to these issues are more than 1,500 satellites slowed down during a great storm in March of 1989. In 1994, 2 satellites shut down during those magnetic storms, and we lost telephone services in Canada for several months. And then during the great storms of October 2003, which we'll talk about in a little bit, we lost 2 satellites, or at least they were severely damaged. But more recently, there's been a more recent event, and that's the loss of, let me just click this here, the loss of 38 Starling communication satellites. These were launched by SpaceX in February of 2022. At first, all things seemed to be going quite well as the satellites were beginning to operate normally. However, a solar storm occurred just a few days later. It wasn't even a major storm, but it was a moderate storm. And that storm increased atmospheric density, which resulted in a significant increase in the drag on those satellites. And ultimately, all 38 satellites were not able to maintain their orbit. So the effects of solar storms on the ground can also be quite damaging. In fact, geomagnetic storms induce currents in the ionosphere that result in magnetic field variations. These variations can cause currents to flow along any conducting path on Earth. These electrical currents are known as geomagnetic induced currents, or GICs. They can surge along oil and gas pipelines and also high tension electricity lines via ground transformers. The extra current in the power lines can burn out transformers, leading to large-scale brownouts or blackouts. While the electricity in pipelines can enhance the rate of corrosion, it's really estimated that transformer failures across, they enhance that corrosion, but it's also estimated that transformer failures across the US and Canada can cause, once again, high economic loss with 100 million in equipment damage that's been estimated in each solar cycle. Here what we show are the results of a transformer failure at Hydro-Quebec, with 6 million people lost power for over 6 hours, over 9 hours really. This was in response to a very large geomagnetic storm that occurred in March 1989, sorry. Next one. So space weather also has effects on radio signals and communication, primarily because those signals meet or transmit through the ionosphere. The ionosphere is part of the Earth's upper atmosphere. You can see that on the left part of this plot. It exists between 80 and about 100 kilometers, and it's where the number of charged ions or electrically charged particles is large enough to affect the propagation of radio waves that are used in our communication and navigation systems. So looking up to the right, on frequencies below about 30 megahertz, our ionosphere actually reflects those signals, allowing for long-distance communication. This was something first brought to society by Marconi in really the late 1800s. So it's been used, of course, since then. But what we also know is that at higher frequency, radio waves pass right through the ionosphere, but not without modifying the signals by refraction and diffraction. So basically it reflects and scatters the signals. And ultimately it changes the speed and direction of those signals. Solar disturbances have significant effect on the ionosphere, and thus introducing additional particles and radiation, making this process even more chaotic. During these events, HF communications such as ham radios and AM radios will be degraded and interrupted. Satellite communication is also affected by space weather. I'll show you this next plot. In fact, it can lead to a total loss of communication, which is due to the attenuation and/or severe scintillation when the broadcast signals cross the ionosphere. The figure that I'm showing you here now was prepared quite some time ago by a friend of ours, and that was Dr. Shani Basu, to show the loss in satellite communication messages in the presence of ionospheric scintillation. Here you can see this is the average signal level. When the receiver levels fade beyond this margin, you basically lose communication. So you can see here the communication message was the quick brown fox jumps over the lazy dog's back. And then as scintillation occurs, we start to lose we start to go below these fade margins, and then you can see you can't even read what that communication message might have been. So in addition to the loss of satellite communication during intense scintillation, we also know that GNSS satellite signals can be degraded, interrupted, and also scintillated during these events. So before we talk about space weather effects on navigation, specifically navigation that's provided by the Global Navigation Satellite Systems, I'd just like to point out some key points about the system. GNSS refers to that constellation of satellites that provide signals from space that transmit positioning and timing data to receivers on the ground or in space. There's currently 4 global GNSS systems: GPS in the US, GLONASS in Europe, GLONASS in Russia, I'm sorry, Galileo in Europe, and then of course there's the Chinese Beidou compass systems, and then Japan and India have 2 regional systems. These systems are designed to provide position and timing information 24 hours a day, 7 days a week under any weather condition anywhere in the world. I'm sure you know of this system as it's now utilized in many of our technologies. What's important to know for us is that GPS signals, GNSS signals, are all quite weak. There's a long distance between the satellite and the receiver, and the signals result in high attenuation of the signal. The signals will be affected by space weather, primarily because they must propagate through the ionosphere. In fact, the ionosphere is the most significant source of error for GNSS. In addition to having to correct for the ionosphere, you know that GNSS has other vulnerabilities, including unintentional interference, jamming, spoofing. We won't go into those details here, just to be aware that they exist. So as mentioned, one of the most dominant sources for GNSS is the ionosphere. And this becomes even more apparent when solar storms, CMEs, and the resulting magnetic storms introduce more chaos into the ionosphere and damaging effects on GNSS signals. The ionosphere introduces ranging and time errors under normal conditions. Space weather can induce larger errors due to strong spatial gradients in the ionosphere. Ionospheric scintillation is the rapid modification of radio waves caused by small-scale structures in the ionosphere. Severe scintillation conditions can prevent a GPS receiver from locking onto the signal, and it can make it impossible to calculate a position. Scintillation can also be introduced during space weather events, particularly in the high and mid-latitude regions, where now we have prompt penetration of electric fields that can induce some of those large spatial gradients and scintillation. So scintillation normally is very rare in the mid-latitudes, really only occurs in response to very, very large geomagnetic storms. At high latitudes, it's more common than at mid-latitudes, and it is increased during magnetic activity. At low latitudes, scintillation is common, and generally it's not induced by space weather, rather by an equatorial electrojet process that emanates from the magnetic equator. Anyway, for ranging areas, for scintillation, all of those other effects for GNSS, this can all result in poor positioning performance, which is the major cause of problem for many of the GNSS applications, such as navigation. So here's an example of some of the large gradients that can be introduced in the ionosphere and in GPS measurements during a significant space weather event. On the left are ionospheric measurements that are taken from a number of GPS ground-based receivers on a quiet day. These receivers were part of the wide area augmentation system that was developed by the FAA to enable civil aviation. The circles on the plots refer to the ionospheric Pierce point locations, and the sticks pointing from those circles is pointing to the GPS receiver, a ground receiver that took those measurements. This plot, you can see, covers much of the contiguous United States. The left plot shows a very quiet ionosphere, where we can see anywhere between 0 and 5 meters of range error over the entire coverage region. The plot on the right, though, shows us a much different picture, with a very strong gradient reaching diagonally over the whole coverage area. So this is known as a storm enhanced density, or an SED, and this has been studied quite widely in the literature. But it was really the first time that we had seen it with WASP GPS measurements. So in a WASP system, what would have happened, and what did happen, is it led to a loss of availability to use the system in this region. And it was primarily due to the decreased accuracy in the position areas that we saw due to that SED event. So the event that we're talking about here is the Great Storm of 2003. We refer to these as the Halloween storms because it was seen during October 29, 30, 31, which of course on October 31 is Halloween. The figure here on the left shows a decrease in accuracy seen from this network of receivers that you're looking at on the right side. In black are the horizontal errors for a WASP receiver, and in color, we're looking at the errors that were recorded on 4 other receivers. These were differential GPS system receivers from the Canadian Differential GPS Network. So here we can see that there's a direct effect on positioning during that major storm. And what we can see is horizontal areas that exceeded, really, you don't see them here, exceeded 25 meters. So here's an example of ionospheric scintillation effects on GNSS signals. On the left, we see measurements taken from Ascension Island. This is an island off the coast of Africa. So on the left are the signal to noise measurements from the L1 GPS signal on the top and from the L2 GPS signal on the bottom. Note that this is really just from one GPS satellite that we're showing you here on the left. And it was using an older receiver, but it's really a great example because this was a time of very intense scintillation at the peak of the solar cycle. So what you see in there on the red on the left is when the signal faded enough that it was not able to use that signal measurement to calculate a position for using GNSS. On the right, I'm showing you the results of the signal scintillation fading on the position that we calculated with GPS. In this plot, Ascension Island is in the center of the plot. And those dots reveal the calculated position using GPS measurements. They are coded according to scintillation level, and those levels are shown in that bar at the bottom. So the highest scintillation level shown is using an S4 of 1, which is quite high. So the resulting position errors really got as high as 75 meters in the horizontal plane and as high as 50 meters in the vertical plane. So ionospheric scintillation fading can certainly affect positioning. This is an example of low latitude scintillation. And as I mentioned earlier, scintillation is more prominent in the low latitudes and in the high latitude regions. Often during solar storms, scintillation is reduced in the low latitude regions. Solar storms, however, can bring scintillation into the mid latitude regions, where it's not generally seen. So this, the phenomena that's responsible for scintillation, as I mentioned earlier, in the low latitudes is much different than space weather. It's due to an equatorial drift emanating over the magnetic equator. Solar radio bursts are also a problem, and these are intense radio emissions from the sun, often associated with solar flares. Studies have shown us that intense solar radio bursts can have a direct effect on GPS signals, ultimately causing position errors. So on December 6, 2006, there was an X6 flare, as I mentioned, X-class flares are the largest. It generated a solar radio burst with measured powers of 1 million solar flux units at the GPS frequencies. This solar radio burst had significant effects on the GPS receivers over the entire sunlit hemisphere of Earth. The figure on the left shows the burst, and on the right, on the top, we see the power spectrum of that burst, and that power went between 1 and 2 gigahertz, the exact frequencies of the GNSS satellites that were operating. And at that time, we see at the bottom, we see significant fading of the GPS signals in the bottom plot. In fact, during this particular solar radio burst, all of the ground-based GPS receivers that operated in the sunlit hemisphere lost tracking capability for about 5 minutes. So as I've stated several times already, one of the most dominant sources of error for GNSS applications is the ionosphere. And that becomes even more apparent during extreme space weather events, when strong gradients that I've shown you in scintillation can further compromise the performance of many applications. So GNSS applications specifically affected by space weather include just about everything we're using in our daily lives, from wireless technologies to cell phones and everything in between. You can see a long list of applications that rely on GNSS and are affected by space weather. So a system that I've had the great opportunity to observe during my career are aviation systems, such as the satellite-based augmentation and ground-based augmentation systems. The ionosphere and space weather are challenged for these systems, and I'll show you that in the next couple of slides. The animation shown at the bottom simply shows that there's been an increasing demand for air travel, and it increases ever so much from year to year. And this increased demand was really a major reason for the development of these new aviation systems. So SBAS and GBAS systems are GNSS augmentation systems for civil aviation. They play a very important role in aviation safety to ensure accuracy, availability, integrity of navigation information. They operate by broadcasting routine correction messages, allowing navigation and control systems to correct for the ionosphere and to provide precise positioning calculations. Large space weather events such as CMEs can induce large errors in the systems, limiting availability of the system. The figures here show that SBAS on the left, you can see that SBAS systems, satellite-based augmentation systems, operate on regional scales, such as the Federal Aviation Administration's Wide Area Augmentation System, shown on the left. You can see that that system covers much of North America, while a ground-based augmentation system, shown on the right, operates on a local area, such as an airport-sized region. So here are some examples of space weather effects that we found on the Wide Area Augmentation System during solar cycle 24. And as you recall, solar cycle 24 was one of the lowest solar cycles of our history. The figure that's on the top left represents a nominal or an undisturbed condition, where we see high availability over 100% of the contiguous US. We see it in about 80% of Alaska and about 95% of Canada. The plots that follow, though, show various degradation in availability during storm days. In the top middle, we see some loss of availability over the CONUS, continental US, and a full loss of availability over Alaska and much of Canada. And we see similar losses of availability over various portions of Alaska and Canada and the US during other storms. I can say that during most storms and most days, really, truly most days, we see conditions such as the undisturbed day in the upper left. I can also say that having studied these storms since the beginning of WAS, we never see quite the same map. You can see here we have 5 other time periods where we had solar storms with various levels of KP, and we always see something different that happens. I've actually not seen 2 alike ever. So we see various amounts. We cannot predict what the effect of WAS on WAS will be just based on a KP value. It's much more complicated than that. So as you have seen, many GNSS applications are affected by space weather. However, significant problems in space weather events are closely tied to the solar cycle, meaning they don't happen all the time. The figure on the right shows the sunspot cycles of the sunspot numbers of the last 3 going to 4 solar cycles. The last full solar cycle that we have had is solar cycle 24, shown right here. And once again, it was one of the lowest solar cycles in over 100 years, much like one that we observed in the early 1900s. So we're currently here on the upward slope of solar cycle 25, where there's already been an uptick in the number of sunspots, together with some flares and CMEs that have induced aurora and some minor effects on society. Predictions originally showed that solar cycle 25 would be similar in size to solar cycle 24, but recent events may change that estimation. The things we do need to be concerned about really are not the average storm or the average day. It's the largest storms, some of which we have referenced in this presentation. The figure on the left shows when these largest events have occurred. You can see that they usually occur near the peak or just past the peak of a solar cycle. These events that have starred there are also listed in the bottom right. The largest storm in history was the Carrington event in 1989. This event actually hit Earth directly, and it caused telegraph lines to spark, really setting fire to telegraph offices. But at that time, as you know, we were not dependent on satellite-based navigation. So that was what we saw, fire in telegraph offices, which of course was very serious. Other storms of note include the March 1989 storm that interrupted electrical power systems in Quebec for an extended period of time. And then I've also mentioned the Halloween storms of 2003, where we saw significant satellite damage, increased levels of radiation, and communication and navigation outages. So although these storms happen near the peak of the solar cycle, I can tell you that they can happen anytime. In fact, there was an extreme event that occurred in July 2012 near solar minimum. This was a huge CME that tore through space really at about 3,000 kilometers a second. In fact, it was 4 times faster than a typical CME, and it was the fastest CME ever seen by the NASA stereo satellite observations. It did narrowly miss Earth. However, if it happened 1 week earlier, it could have been a direct hit. This computer model that I'm showing on the left shows the location of Earth, right here. Location of Earth is right there, with the sun in the center, and the CME plasma cloud right here, hitting the Stereo B spacecraft. That turned out to be a good thing as it happened, because the measurements since then have verified that this was a CME that could have rivaled the 1859 Carrington event, really the largest we've ever seen. A study that was done following that event by the National Academy of Science found that a Carrington event today could cause significant damage, really damage worth well over $2 trillion in the North American continent alone. And it could take us years to make the repairs. The reason is that much of our infrastructure and technology is dependent on satellite and space technology. GPS communication systems, aviation systems, the internet could all suffer some damage in the face of a Carrington event. So even during quiet times, big storms can happen. Thus, we all need to be prepared and aware of what this is. So, as I mentioned, space weather is important. I think we've all appreciate that. Research indicates that severe space weather has the potential to disrupt our critical infrastructure with significant consequences. As such, governments have been preparing. Governments around the world, including South Africa, I might add, have responded and are working on and have produced space weather strategies and action plans. The US released their first strategy and action plan in 2014. This was updated in 2019 with a cohesive all-of-government plan delivered to really mitigate, respond to, and recover from major space weather storms. More recently, the Pro-SWIFT Act became public law in October 2020. The purpose of that was to mandate work to improve the ability of the US to forecast space weather events and mitigate its effects. As mentioned, other nations are doing the same, as they are working together as space weather is really a global concern. An example of this collaboration and the success of the collaboration is the International Space Environment Service, or ISIS. This includes 21 regional warning centers around the globe. Their mission is to improve, coordinate, and deliver operational space weather services. ISIS is organized and operated for the benefit of the international space weather user community. Here on the right is a picture of the US Warning Agency at the Space Weather Prediction Center, SWPC. And if I just flip to the next picture, I'm showing that there is an ISIS center that was in development at SANSA when I was there 3 years ago. I got to visit the center before the pandemic. And as I understand it, and as Leanne has mentioned earlier, the South African Center will become fully operational in October. So congratulations to all of you on that. So in addition to awareness and mitigation plans, it's also good to note that research is also very active. NASA and other partners operate a system observatory of heliophysics missions, utilizing the entire fleet of solar heliophysics and geospace spacecraft to deliver the processes, to discover the processes that work throughout the space environment. Some of the examples of the most important satellites for us include the ACE measurements of interplanetary, it's studying the interplanetary conditions. We get CME alerts from SOHO, shown here. Stereo beacon images at the far side of the sun. Here's a stereo satellite. And of course, we have the SDO, where we see high resolution images. Most recently, launched in 2018, was the Parker Solar Probe. This is a robotic satellite to probe the solar corona, really getting as far close to the sun as it possibly can. And this is also observed the start of solar wind. So another important element when thinking about space weather is really public outreach. And this is one of the reasons I'm happy to talk to all of you today. So over the last few years, there have been efforts to build public awareness of space weather. The average space weather storm could occur at any time, and we probably won't even know it happened. If anything, these storms may have caused a blip in the electric grid or a buzz to our ComNav systems and produced some pretty aurora in the high latitudes, but it certainly isn't something to disturb our everyday lives. However, what you might see sometimes are frightening headlines like these, but please don't panic. Just be aware and know that there are programs in place and in development to predict and mitigate the effects of solar storms. I actually tried to collect some of these crazy headlines and show you a few here. Ending civilization, a catastrophic solar storms, and threatening life as we know it on Earth. Certainly, if we have a major storm like the Carrington of 1899, we'll all feel it, but it's not going to end civilization. So I live in New England, where winter snowstorms can be quite disruptive. We can get close to a meter of snow sometimes that could limit our lives for a few days at a time. However, we see terrestrial weather reports, such as the upper left, gives us advance notice. Certainly terrestrial weather modeling and prediction is far advanced from space weather modeling, but we do get lots of advance warning about these winter storms. And we prepare for those storms. We prepare by ensuring that we have, a water and food supply for a couple of days, an alternate heat and power source. We stock up on non-perishable foods, and we plan a communication plan with our family. I tried to find a good picture of a storm in progress, but the only thing I could find on my phone was my backyard in January of 2022. So you can see we get quite a bit of snow here in the Northeast, but we plan for it. In the recent past, I was glad to hear this past year, a news report on the local news channel that talked about a potential solar storm. It really was only suggesting that we stay up late that night to watch for Aurora in the New England region. I expect that if an extreme event was on its way, and these are going to be very rare, we would get more precautionary warnings to prepare for outages in our electric grid and our communication navigation systems. The clip I'm showing you here on the right was from the National Weather Service in the US. And as you can see, they're already giving information on how you can prepare for an extreme solar event. So in summary, we've covered a lot here. We've discussed the physical concepts of space weather that included the sun, the solar wind, the solar eruptive events that are known really as the sun-earth connection. We observe space weather impacts, radiation, power grid disruption, satellite damage, and what we see on our GNSS applications, primarily because those satellite links go through the ionosphere. With that, we see great influence from space weather. We also demonstrated solar activity in the solar cycle. Told you that most big storms occur near the peak of the solar cycle, with a few exceptions. We also discussed something very important. That's the international efforts that are underway to mitigate and to forecast space weather. Also, just something I'd like to stress, that it's important that we advance public awareness of space weather and to let everyone know that research is continuing, predictions are getting better. With that, I thank you very much for your attention. This is my contact information. I'm happy to chat with you at any time. And I thank the Federal Aviation for their support under a cooperative agreement to perform much of our space weather work. And with that, I can restart my video. So thank you all.
Yeah, thank you very much, Pat. That was fantastic and a good talk as always. I would just want to appeal to our audience. If you have any questions, please type them in the Q&A. The Q&A button is at the bottom, and I'm sure Pat wouldn't mind answering a couple of questions live. We have one already in the chat from an anonymous attendee who says, "Great presentation. I would like to know how pipelines are affected by space weather."
So space weather, the disruption of the pipelines, what it does is it causes corrosion. So as you know, it can affect really any kind of, hold on one minute. The particles actually come through, they can affect any kind of a pipeline or network, cables or any type. But the effect on them, I don't know the exact mechanism how it affects those, but the result is really the corrosion on those pipelines that occur.
Thank you very much. The questions are coming in now. The next one goes, have any plane crashes resulted from the failure of Geonenesis satellites during these storms?
No. The systems such as the wide area augmentation system and other systems around the world are set to detect when there's a gradient or to detect when there's scintillation. And basically when that happens, it limits the availability of the system. And it has been 100% successful. What happens to those aviation systems is you lose availability to use the system. Now, one of the benefits of those systems is it really matches the capability of an instrument landing system. Instrument landing systems, which is what most airports currently use, bringing aircraft to 200 feet above a runway. And then the pilot uses visual guidance to bring it to the ground. These systems, such as WASP, do the same thing. So ultimately, a lot of those instrument landing systems are now complemented by wide area augmentation or SBAS type systems. Ultimately, the plan is some of those instrument landing systems will be replaced by it.
Thank you very much, Pat. And I can add to that in Africa we are still using GBAS, not SBAS, and in most of our African states. So we're working on convincing the authorities to go the SBAS route as well, but then also to be aware of space weather.
Yes, they do.
Some more questions. The next one, do you have any documented anecdotes of space weather impacts on radio altimeters in aviation?
I don't, but I think there is a connection, and I'd be happy if you want to contact me. I will look it up and get you that answer. But I don't know I know there is an effect, but I can't give you a documented evidence of it just yet. I will look it up for you.
Thank you. Thank you. The question came from Pierre Cilliers, who you know very well.
Of course. Hi, Pierre.
Then the next question is, what is the current accuracy of space weather forecasts versus time ahead?
So you can see those big CMEs, right? The ones that are the most damaging, creating the greatest effect. We see them coming. I mean, you know they're coming. You can see them coming, 4 or 5 days in advance. What we don't know is where it's going. Generally, that solar wind, as I said, goes all the way out to interstellar space. As they're forecasting and watching this coming through, we know it's going to hit. We don't know how intense it will be. We don't know what the big damage will be. Sometimes it depends on, the time of day that it hits as to what's going to happen. But certainly we can see CMEs coming. Solar flares, not so much. Solar radio bursts, they come in instantly. So being able to, it's hard to forecast something that happens instantly.
Yes, thank you. The next comment, thank you for your wonderful presentation. My question about how the current can produce scintillation. My information is the main source is ionospheric irregularities.
How it produces scintillation?
Yes, the question is worded how the current can produce scintillation. So I think that the person is asking about the main source of ionospheric scintillations. Is it irregularities or?
It's irregularities, yes. The ionosphere is always chaotic. I mean, it certainly changes the speed of the signal. It also refracts it. But when there's bubbles, bubbles emanate from the equator. They come up, they generate out to an equatorial region, which is north and south of the magnetic equator. I didn't get into that today, but those bubbles actually get into that ionosphere, and they generate irregularities, and that's what causes scintillation. It's really gradients in the ionosphere, very small gradients in the ionosphere, which generate scintillation.
Thank you, Pat. Another question. From your presentation, space weather is not a regular occurrence. How then do we go about forecasting the event?
Space weather happens all the time. Most of the time, it's not a big deal. But centers such as the ISA Center in SANSA and Space Weather Prediction Center, they're always watching. As I showed you in that NASA plot with all the satellites that are out there, they're always watching what comes off the sun. And those big events will be forecasted. They're seen and they're forecasted in that they're coming towards Earth. We can't forecast they're going to happen on the sun. That happens when the sun releases it. We're not at the point where we can forecast what the sun's going to do, but we can see when it happens.
Thank you. And then there's a question which I think I'm going to have to answer. The question goes, I want to ask if you're interested in doing research in space weather, how you can apply to pursue with master's research at SANSA. And that's why I'm thinking maybe I should answer that one. So if you go to our website or you go to research.sansa.org.za, you will find the contact details of our researchers. That's your first port of call to find a researcher with a project that you would be interested in working on. Then you can contact that researcher, and you can also contact our student administrator or student liaison office, and I'll put the email address for her in the chat so that you can contact her. But I would look out on our website as well. We do have a bursary program for masters and PhD students, and that is usually advertised through our website and on Twitter. But do get in touch with us if you're interested in doing your masters or in pursuing space weather research, and we'll definitely help you out. And then, Pat, there's one, I think this will be the last question that we'll take for today. Okay, so this is, what is your opinion on the current solar flare on its way to Earth as reported on, and then they've given a link, but it's actually a news report from express.co.uk about the solar storm warning hitting Earth today, cracks open magnetospheric space weather.
So I think I brought it up on the screen. Can you see it there? I think it's on the screen here now. This was just released yesterday. Solar storm could hit Earth today as crack opens in magnetosphere. Scientists baffled. I haven't read the whole article, but once again, I wonder if it's one of those scare tactics that I had shown you earlier. You know, crack in the magnetosphere. I don't know exactly what they're talking about. Scientists are baffled. I'll have to read this and see what the whole article says, but I haven't looked at it just yet. But once again, sometimes, you know, Express News and some of these other online news sites, they're looking for the headlines.
Yes, yes, absolutely, absolutely. Okay, well, I think I'm going to, I'm just going to quickly type into the screen here, or maybe I'll ask Dillian to do that while I sign off. Dillian, can you just put into the chat the Space Science Information Web email address for anybody who wants more information? And then I'm going to thank you very much, Pat, for your time this afternoon and for joining us. I do want to notify our audience of our next, let me just find the picture now, of our next Space Talk. Our next Space Talk will be, I'm going to see if I can share it with you now. Our next Space Talk will be, can you see it on the screen? Oh, wait, I've got to click share. No, it's not working. Don't worry. Can you see, Pat, the webinar advert?
I can see it, yes.
Okay. So our next Space Talk will be on Wednesday, the 27th of July at 3 p.m. And it will be given by Prof. Mike Kosh on atmospheric optics, rainbows and other magical lights. And as you can see, he calls himself the director of fun. So it's definitely going to be something to watch out for. So with that, I would like to thank our audience for attending, for supporting the SANSA Space Talk. Thank Patricia very much for giving up her time this afternoon, your morning, for and giving us such an interesting talk on a fantastic topic that we're also very excited about here in South Africa. So thank you very much.
Thank you. It's my pleasure.
Thank you. Okay, and a very good afternoon to everyone on the call. Thank you. And Dillian has put some information there.